Okay, back to our lecture. We'll get back to that demo in a moment. Okay, so let's put some numbers to this. Let's take a current I1 that is no longer constant, but let's allow it to vary in time. So let's make it cosinusoidal at frequency omega with amplitude I naught. Now we'll take our expression for the EMF induced in coil 2, do the time rate of change in coil 1. It's proportional to this mutual inductance, which we just calculated. So I have an expression I can plug in for this M. Right, there it is. di dt I can figure out. I can take the time derivative. Time derivative of a cosine is a sinusoid. So I get minus sine, and then I bring the argument out. Right, take the derivative of the argument, I get an omega. So I'll plug in this term down here. This minus sign and that minus sign cancel. I get plus. And I get an expression for the EMF in coil 2. Because my current is varying, now I have an EMF in coil 2. And I can plug in some numbers. I'll plug in a 1/2 meter long solenoid with a 10 centimeter square area, so something like this, with 1,000 turns in one coil and 10 turns in the other. And I'll put 5 amps through at 60 hertz. So these numbers are fairly large. 5 amps is a lot of current. A household circuit can deliver about 15 amps before it blows its fuse. 1,000 turns obviously is a fair number of turns. A 1/2 meter long device is something that's not going to fit on a circuit board. And all of that gives me an EMF of only 47 millivolts. So we're not getting a huge amount of voltage produced, a huge EMF in the secondary coil. So you can power your toothbrush, you can recharge the battery, but you don't yet run your laptop wirelessly from across the room using inductive charging. It turns out, though, there is a case where you can get much, much larger EMFs. And that is where the current is not changing smoothly, but when it changes much more abruptly. And that's what happened in that demo when the switch was opened. The current changed from whatever it was to 0 very rapidly. So we'll do a demo of that, and we'll cover that in a minute. What was shown in that demo, in that video, is actually an example of self-induction, not mutual induction. So self-inductance is a similar process to mutual inductance, but it's where you only have a single coil. And some current in this coil produces a flux through the coil. And if that current changes, this coil itself will have an EMF induced in it that tries to oppose the change in flux. So now, instead of having two separate coils where the change in current in one produces an EMF in the other, we're saying the change in current in the first produces an EMF in the first. And so we can express the relationship between the induced EMF and the change in current in exactly the same way we had before. Before we said that EMF was minus m di dt. And now we'll just replace that minus m, that constant of proportionality that talked about the coupling, the magnetic coupling between two circuits. We'll replace it with this constant L, which is called the self-inductance. Or more commonly, it's just called the inductance. But that constant M, the mutual inductance, depended on the area, the size, and the location of these two coils relative to each other. Now, if the coils are co-located, you basically end up with specific geometry, and we call that specific coupling L, the self-inductance. And so this can be a useful effect. If you try to change the current in this coil, it produces an EMF, a voltage. So that can be a useful element to have in a circuit. We'll see in a minute why that could be useful. Perhaps a straightforward way we can understand that right now is if you try to produce a change in the current, it produces an EMF that opposes that. So a coil of wires tends to, I hate to use terms that are usually used for creatures and live beings, but it tends to want the current to remain constant. And the physics is such that the current, it becomes difficult to change the current, because in attempting to change the current, the self-inductance produces an EMF that opposes that. So these coils of wire are used commonly to smooth out fluctuations in what should be a DC power source. And this relationship between the induced EMF and the change in current looks exactly like that we saw for mutual inductance. This self-inductance we can define just like we did the mutual inductance. It's the total flux through the coil relative to the current in the coil. So N times phi is the total flux. Phi is the flux through one loop. N is the number of loops. And if we divide that by the current producing the flux, we get that constant L. So these devices that exhibit self-inductance can be useful in circuits. We call them inductors. They tend to look exactly like what you would expect based on the schematics we've been showing and the diagrams we've been showing. They tend to look like coils of wire, usually wrapped around an iron core. And oftentimes that core is toroidal, so that the circulating field loops in around itself, and you don't get magnetic leakage that can induce interference in neighboring parts of the circuit. So you often see these things the size of a coin or so. If you open up a lot of different electronic components, anything that has high voltage in it, things that have tuners, so radios, television sets, computers, generally will have these things on the circuit boards, as well as anything that's going to have plug into a wall but requires DC power. You see these inductors in the transformers that convert the AC to DC. In the next chapter, we'll talk about the process that occurs there. So these are what the circuit elements look like. This is what the diagram looks like. It's sort of a schematic of a coil. And since so many of these are toroidal, let's consider a toroid geometry. Let's say there are n turns of wire around this ring of radius r. Then let's find the self-inductance of this device. So to do that, we need to know the number of turns. We're given that. The flux through the cross-sectional area, and the current going in. So first we need to know the magnetic field through the core. And then when we multiply that by the area, we will get the flux. So the magnetic field through a solenoid, we already said mu naught Ni, where N is the number of turns per unit length. And that's in a solenoid. If we have length L, we can write the number of turns per unit length as the total number of turns divided by the length. So this is for a solenoid. For a toroid, we have basically the same expression. We're just going to take our solenoid and wrap it around a circle of radius r, so that what we were calling L before, we will now write in terms of the parameter we're given, r. So this L is 2 pi r. It's just the perimeter of our solenoid. And so we get this for the field inside the toroid. If we multiply that by A, we get the flux. And once we know the flux, we can divide it by the current that produces it to get the self-induction. There's an error on the next slide. This right here should be n phi over I. N phi over I. There's phi. If I multiply it by n and divide it by I, this n becomes n squared, and that I goes away. And I have this expression. Little I is the current. The more current we have, the more flux we have, but the self-inductance gets normalized by that. So it's a purely geometrical effect and doesn't change with the amount of current.
There's a limit of how much current you could put in that sunlight?
Yeah, I mean, if you put in too much current, you'll tend to heat this up. And then what happens is, so I've done this several times today. You saw any smoke.
How can you find the maximum current?
Well, so you have wires of a certain gauge, a certain area. Okay? If you know the resistivity of the material, then you can find out how much resistance there is for a certain length of the wire that you've got in your solenoid. Once you know that resistance, you can start putting current through and saying the power it's going to dissipate is I squared R. So as it dissipates that much power, it's producing heat. That heat has to go somewhere. Okay? If you connect this to a heat sink or you put a fan on it, you can take that heat and carry it away and keep this cool. If you can do that, you can put more and more current through. If you don't do that, the heat goes into heating up and changing the temperature of this. And as it gets hot, what happens is you start to melt the insulation around these wires. And that produces that blue smoke that appears when you start playing around with these demos sometimes. I may do that more than you do. I've seen a lot of blue smoke today. And then once the insulation completely burns up, then you get a short between the wires, and then it stops acting like a solenoid. You just the wires touch and the current just goes zip right around. So basically, you can do some calculations to try to figure it out, but in reality, if you buy this, it'll come with a rating that tells you. And if it doesn't, you can build 2 of them and take one of them and turn up the current until it stops functioning, and you know the limit on the second one. Okay, so these inductors, we can look at this expression and we can say, if we have current going through an inductor, and we suddenly remove that current, or we suddenly turn off the current, then we get a di dt at the instant that the current changes, and that produces a voltage. And that voltage can power a device. It can induce, it can cause additional current to keep going even after we've disconnected a circuit. So there must be some power, some energy stored in the inductor that provides that. And in fact, there is. It's stored in the magnetic field. Okay? We can understand that by looking at the power delivered to the inductor. The power is always, electric power is always current times voltage. And I'm going to use the convention that your book uses of writing a lowercase letter to represent a time-varying quantity. So we usually use I to represent current. I'm using lowercase I to denote that that's a current that is going to change. Okay, so power equals IV. The voltage, in this case, is the EMF of the inductor, which is just L di dt. So you can see that if the current isn't changing, the power delivered to the inductor is 0. But if the power is changing, then this is non-zero. The power will be non-zero. And so as the current changes, we can figure out how much energy gets deposited in the inductor. So the energy is just the integral of power integrated over time. So I'll integrate from some initial time 0 to some final time t. I'll write power as IL di dt. So IL di dt times dt, and the dt's cancel out. So I'm left with IL di. So now I'm integrating with respect to I, not with respect to t. So if my time goes from 0 to t, in that time, I'll say the current goes from 0 to some maximum value. I'm saying I'm turning on the current. As the current builds up in the inductor, how much energy gets stored. And this will give me an expression then for how much energy gets stored as a function of I, the current flowing after some length of time. So L is a constant. It comes outside the integral, and I'm left with the integral of I. So I get I squared, take the power there and put it in the denominator. I'm left with 1/2 Li squared. And I evaluate that at this limit, I get this. I evaluate it at this limit, and I get 0. Okay, so the energy starts at 0 and ends up with 1/2 Li squared. So this is how much energy is stored in the inductor. So where did that energy go? I already said it 1 minute ago. Not heat. If it goes to heat, it's lost. It's stored somewhere. We can get it back. We will get it back if we take this circuit that was pumping current through the inductor and I suddenly remove the battery. The EMF, the quick time change, the quick change of the current will produce an EMF that can continue to power the circuit briefly. So the energy is stored and can be retrieved.
What purposes is that useful?
It's useful for like a surge suppressor. Rapid changes of current get suppressed. Even if the circuit suddenly turns off, the energy stored in the inductor can continue to power the circuit for a brief period of time. So what are my options? If it's not stored as heat, where else could it go? Yeah, it's stored as magnetic flux, stored in the magnetic field. So there's a magnetic field that gets produced as the current starts to go through this. And when the current is I, there's a magnetic field going through proportional to I. That field takes energy to produce that field, so that field has energy in it. Okay, so we can relate that energy to the magnetic field by considering this example of a toroid. It turns out the expression that we'll derive is more general than this, but it's useful to have a specific geometry to derive how much energy is stored in the magnetic field in terms of the strength of the magnetic field. We said the inductance of the toroid we just calculated, mu n squared a over 2 pi r. We have an expression for the energy stored, 1/2 Li squared. So now we'll plug this value for L in here, and we get an expression for the energy stored in terms of the geometry of the toroid and the current through it. Now we can use our calculation of the magnetic field that's related to these geometric properties of the toroid. So that's over here. The magnetic field through the core is mu naught n I over 2 pi r. And if I look at this expression I have up here, mu naught n over 2 pi r appears in that expression. So I can just take mu naught n over 2 pi r times I and replace it with b. And I will do that. And I will also take the total energy stored and I'll divide it by the volume of space in which the magnetic field is confined. And that will give me the total amount of energy per unit volume. Okay, so dividing this by the volume of this core, if the cross-sectional area is A and its length is 2 pi r, that means I can divide this by A times 2 pi r. That gets rid of the A, and dividing it by 2 pi r makes that 2 pi r squared. And I'll call that the energy density. And now this n squared I squared over 2 pi r squared, n squared I squared over 2 pi r squared, looks a lot like b squared. I just need a mu squared. So I'll multiply this by mu and divide it by mu, and then replace all these terms here with the b squared. Then I get an expression for the energy density stored in the solenoid that depends on the magnetic field. And so what's kind of interesting here is I derived this based on this specific geometry, a toroidal solenoid. But the expression that I got, the energy stored per unit volume, depends on the strength of the magnetic field and the material that that magnetic field is in. And nowhere in here does it say anything about the geometry of what produced that magnetic field. So although I calculated this for this geometry, this particular toroid, I could consider it for a solenoid or a loop of wire or just a permanent magnet with a magnetic field B. Over a region of space where the magnetic field is B, the energy stored is B squared over 2 mu per unit volume. So I'm using a specific geometry to derive a general result. We already saw when we looked at parallel plate capacitors that when you charge up a capacitor, the energy you put into it gets stored in the electric field between the plates. And we could write the energy density of the electric field. And here we have a similar thing, the energy density of the magnetic field. So electric fields and magnetic fields store energy. So this will be really important. The last chapter that we cover, we'll talk about electromagnetic waves. And we'll see that they are fluctuations in the electric and magnetic field that propagate away energy. So light has energy, propagates it away, and it's because of this. It's because the electric and magnetic fields can store energy. Okay, so getting back to our circuit, how can this be used, and what does this do for us? So in order to understand how an inductor will behave in a circuit, we're going to use the same rules that we've used for understanding how everything else behaves in a circuit, mainly Kirchhoff's rules. So in order to do that, we need to know how the voltage changes when you go across an inductor. And the voltage change is just the EMF of the inductor. Right? So the EMF of the inductor looks like L di dt. And we'll say if you're going in the same direction as the current, then this represents a voltage drop, just like we have with resistors. For a resistor, if you're going in the direction of the current, Ohm's law V equals IR gives you the voltage drop. So this is a voltage drop. Okay, that's a voltage drop, assuming this is a positive number. Now, di dt can be either positive or negative, depending on whether the current's increasing or decreasing. So you could have a negative voltage drop, which would be a voltage gain. But our convention will be, if we're going in the direction of the current, and this expression evaluates to a positive number, then the voltage decreases going across the inductor. Okay, so this would be increasing. That means if your current is increasing in the direction of the current, you get a voltage drop. Let's see if we can understand that. If we have this inductor here, let's say we have current going left to right. As we go across this inductor, if the current is increasing, di dt is positive or negative? Positive. Okay, so the current is increasing, di dt is positive, we get a positive voltage drop. We got the voltage here being higher than it is there. So the voltage here is higher than it is there. That's going to now I've confused myself. That's not helpful. All right, I'll have to come back to that when I'm not confused. I'm either confused or I've done something incorrectly. But let's apply this to actual circuits. So let's consider what we call an RL circuit. This is sort of the simplest circuit we can design with an inductor in it. We've got a resistor, R, and an inductor, some induction L, some inductance L. And we'll connect this to a battery with a switch so that we can turn the circuit on and off. If we didn't have this switch, then whatever the steady state current in the circuit was is what we'd have, and there'd be no change in that. So we know that it's only when there's a change in the current that this inductor does anything. So we'll put this switch in so we can open and close it and see what happens. And we'll also put a switch in here to short out the battery, so to sort of remove the battery from the circuit. And essentially what this is going to do is when we have the circuit as shown, where this switch is closed and this switch is open, then the battery will drive current around the circuit this way. As it does, the current flows through this inductor. It starts to build up a magnetic field here. And then if we open this switch, that magnetic field is going to produce an EMF that's going to oppose that change and going to try to keep current flowing in the same direction. And then if we close this switch, the current can now flow around this loop. No longer powered by the battery, but now powered by the inductor. And the energy stored in the magnetic field produced by the inductor, trying to keep the current flowing because of Faraday's law. Okay, so first considering this example of the outer loop with this switch closed. Applying Kirchhoff's rules, going across this battery, we have a voltage gain of E. Going down this resistor in the direction of the current, we have a voltage drop of IR. And then going across this inductor, we're going in the direction of the current, so we get a voltage drop minus L di dt. And we end up back where we started. So the total voltage drop across the loop is 0. So now we'll rearrange the circuit. And what I want to do is solve for the time rate of change of the current through this inductor, or in the circuit. Okay, so I'm going to be interested in solving for I. And we can see that it depends on time, so there's going to be a time dependence to it. So this is a differential equation. It's one that's particularly easy to solve, though. It's a first-order differential equation. So, all right, what did I do here? I rearranged this to get all the terms that depend on I on the left side. So I had divide all the terms by L, or by R. Bring this term to the right side, divide it by I, and I'm left with this expression. On the left side is everything that depends on I. On the right side is everything that depends on T. And now I can integrate both sides. So on the left side, I'll integrate with respect to I. And I'll start with no current flowing. So that would be with this switch open. There's no current flowing. And what I want to find is, what is the current in the circuit after I close the switch? So at time 0, the current is 0. And at time t, I'll say the current is I. So I'll integrate current from 0 to I, time from 0 to t. This integral is straightforward. It's just a constant. So when I integrate that with respect to t, I get that constant times t. This integral, di over I, looks like natural log. So when I integrate that, I get natural log. I can use substitution to say this denominator I can call u. The derivative of the denominator is just di, so the numerator I can call du. And so I've really got the natural log of this denominator, which when I evaluated I get I minus e over r. And when I evaluated 0, I get e over r. So I get the ratio of those two things. And now I can take both sides. I can take e and raise it to this. And e to the natural log of something just gives me the something. And e to this is what's left on the right side. So there's the something, there's e to the something, e to the to the right side. And I can solve this expression pretty easily now, algebraically, for I. Okay, so here's my final expression. The current flowing in the circuit is a function of time. At time 0, this term is equal to 1. 1 minus 1 is 0. So at time 0, there's no current flowing. That's when the switch is open. There shouldn't be any current flowing because I haven't closed the switch. And then the moment I close the switch, I would normally expect to have current flow through the circuit. But the moment I close the switch, as that current tries to flow, it produces an EMF in this coil that opposes that. And as a result, current does not flow initially. Hence, at time 0, there's no current flow. And then as time continues, the current slowly starts to build up. So this restricts the change of current. So it doesn't change instantaneously. Instead, it takes some time to build up. And it will eventually get to the point, so in the steady state, when there is no change in current, the voltage drop across this is 0. If the voltage drop across this is 0, I just have a battery and a resistor, and I end up with a current that's equal to E over R. So that's the steady state value. It's approaching that asymptotically. I can see that from this exponential behavior. And I can define the time it takes it to approach this using the time constant. I can call the time constant the time it takes for it to reach 63% of its final value. That's the time where this exponent is minus 1. Right, so I'm requiring the height here equal to times 1 over E. I'm setting this exponent to minus 1. That means T has got to be L over R. So evidently, it has units of seconds. There's dimensions of time. And L over R for an RL circuit is the characteristic time it takes the current to change to 63% of its final value. So the presence of this inductor causes the current to restrict changing. Any perturbation of the circuit that tries to change the current in it will eventually do so, but it will do so over a time scale of L over R. If the inductor is not there, then L equals 0, and the current can change instantaneously. But the bigger the inductor, the longer it will take it to change when there's some external perturbation. So this is the current building up. Now I can consider what happens when I close this switch. So I have current flowing through this inductor. When I close the switch, without the inductor there, you'd say, well, now no current flows, because if I just look at this loop here, I have no voltage source to drive current across that resistor. But with the inductor, the voltage source is the EMF associated with the change in current. So I close that switch. That causes the current to want to go to 0. That very rapid change in current produces an EMF that continues to drive current through the circuit. So even after I've closed the switch, current keeps flowing through the circuit. The inductor acts like it gives inertia to the current. Current can no longer stop instantaneously or change instantaneously. It takes time to do so. So we can work out the rate at which the current will decay to 0. We look at Kirchhoff's rule around this loop. If the current's going left to right, we have a voltage drop of I dl dt, di dt times L across the inductor, and then a voltage drop of IR over here. And those voltage drops have to equal 0 because I go around a loop. So put the I's on the left side, the T's on the right side, just like I did before, and then I can integrate both sides. But now if I start at time 0 and I go to time t, I'm assuming that my initial current is not 0, but rather some value I naught. And I'm interested in finding little I, the current after some length of time. So the integral of this is just natural log of I. And when I evaluate that at the limits, natural log of little I minus natural log of big I is just natural log of their ratios. When I integrate this, this is just a constant times dt, so I get that constant times t. And to get rid of the natural log, again, I take e and I raise it to the left side and set it equal to e raised to the right side. So e to the natural log of this is just this. And e to the minus r L over t is what I'm left with on the right. Multiply both sides by I naught, and I get an expression for the current as a function of time. At time 0, this term is 1, and the initial current is just whatever it started as. But as time increases, this value goes down to 0. It takes a time L over R before it decays to 1 over E of its initial value. But it asymptotically approaches 0, so I get a current that looks like that. Instead of suddenly turning off when I close that switch, it now takes some time as the magnetic field that's built up drives current to flow, and in doing so, the magnetic field decreases, and the current carries away the energy that was stored in the magnetic field. Fred?
Why would you use that instead of a capacitor?
Usually you wouldn't. Most devices use capacitors, not inductors, to achieve the exact same thing. Okay, so these are not very commonly used in circuits. They tend to be larger than capacitors, physically larger. They take up more space. They tend to be lossier than capacitors because the resistance in the wire dissipates energy that you don't have a problem with in capacitors. And they tend to be heavier because you tend to have these iron cores to concentrate the flux as opposed to some lightweight dielectric like mica. So for all those reasons, capacitors are more practical, and you rarely see inductors in circuits. It's an example. There are a few specific applications where inductors are used. And so we have to understand, first we understand the RL circuit, then we'll understand the LC circuit. And this is really where inductors do get used. Before we move on to the LC circuit, though, I can do that demo that I showed you the video of. I'll show the video one more time. We can understand it a little bit better now. Let's see, this is a giant inductor. So the two solenoids, just a big inductor. There's a resistor. This is an RL circuit, and that's our switch. There's a power supply that puts 30 amps of current through this. And so when that switch is opened, that current wants to stop. It no longer can flow. I mean, opening the switch does stop the current. Current can't flow because there's an open circuit. But the inductance tries to keep the current flowing. You can think of it that way. And it generates an EMF that opposes that rapid change in current. And that large EMF produces a high voltage between these two terminals that actually causes an arc. So it breaks down the air, ionizes the air, and allows the current to flow through that ionized channel. That's basically lightning. Right? And so the current keeps flowing even though there's no longer a metallic contact here. It breaks down the air and flows through the air to complete the circuit. So that's just an example of how much the inductor will try to keep the current flowing. Yes?
What's the purpose of the resistor in that circuit?
It limits the maximum amount of current. Okay, so I'm going to do this demo here as well. Let me explain what I've got. It's actually a very simple demo, but I've got a lot of pieces to it. This box right here is my DC power supply. It can put out about 5 amps, so nothing close to the 30 amps used in this demo. Then it gets wired over to this box, which is a resistor. It's set at 6 ohms, so there's not very much resistance. It turns out if I lower this, I get more current through and a bigger effect. And I also start to melt things. So that's good. Remember what I said about keep trying it until you do one that doesn't break? 6 ohms. OK, so through this resistor, then it goes to this. This is a transformer. We'll talk about transformers next week. But for our purposes, right here, this is an inductor. This is an inductor. It's got an iron core that channels the flux around in a circle. These are also inductors. They're toroidal inductors. And I just have them in series to increase the total amount of inductance. So I have from this resistor to this inductor, from this inductor to this one, from this one to this one. And then I go all the way back to this switch. And then to the power supply. So when I close the switch, current flows through. I only get about 0.5 amp of current going through. Turns out more than that, and I start to melt things. So the first thing I can do is close the switch. Current's flowing through. There's no way for you to see that right now. But you can see what happens when I open the switch. It's not quite as dramatic as what happened in that video, but it's the same effect. OK, so I'm generating a spark. There's only like, what is there? There's only a couple of volts driving this circuit. But because all I've got is basically wires and 6 ohm of resistance, a couple volts can drive a whole lot of current through this circuit. And then when I break this, I'm very rapidly changing that current. So there's a very large di dt. So there's a very large EMF that builds up due to the inductance of these three times that di dt. So the EMF that builds up can be much larger than the voltage that I was initially driving the circuit with. Now, it doesn't last very long. It, in fact, will build up. It will build up until it's large enough to ionize the air. Then it will discharge, and the current goes back down to 0. And that EMF goes away. So it's not like I can generate a high voltage, steady power supply this way, but I can generate very short, instantaneous, high voltage peaks. So let me demonstrate that. OK, I have over here that's annoying. Let me fix that. I have here the display of this oscilloscope. And it's going to update every 3 seconds. It's just doing a screen capture of the oscilloscope and sticking it up there. We don't see anything very interesting right here. What I'm looking at is the voltage across the switch. So these 2 leads right here go to this box, and then from this box go to the oscilloscope. This box is a voltage divider. It's just a pair of resistors that are set up to reduce the voltage by a factor of 10. So right now, I have 0 voltage going in, 0 voltage coming out. We see a nice 0 line on the oscilloscope. This little indicator right here is the trigger. It's going to freeze the oscilloscope display anytime this current, or this voltage exceeds this level, which it's not doing right now. But if I allow current to go through, and then I break that current and give it 3 seconds to refresh, I didn't hit return. Wow, I'm glad I spent an hour of my life setting that up. That's not what I see on the display over here, so I know the experiment worked. One worked when I did one. Let me just reload the page. See what that does. Yeah, I can do that, except that the oscilloscope is actually not showing what's on the display there. Yeah, I am hitting refresh. I'm just doing it with the keyboard.
Why don't you just put the oscilloscope over to the back?
Because I spent so long trying to set this up. I had to like reconfigure the network on this, type in a manual IP address, set this up for a crossover Ethernet connection to that. And it's just, I want to actually see it. I just want to see if it's talking to it, maybe. All right, you in. You see that? You see anything change? Okay, I'll make it a little more obvious. I'll reset the display. I'll do it again. Okay, so you see that peak. So what I'd love to show you, I'll keep hoping. This is a little harder to see. That peak is 400 volts. So I'm getting 400 volts. That's why I had to divide this by 10, right? If I had not done that, I'd damage the oscilloscope. That 400 volts is much larger than the 2 volts that I'm driving the circuit with. But because this change in current is so quick, for a very short instant in time, and you can see that on the oscilloscope, it's only a very short spike, but I get this big peak. You've probably seen this effect yourself if you've ever unplugged a refrigerator or anything with an electric motor, an air conditioner. You ever unplug it and see a spark? Okay, that's what you're seeing. It's unplugging it just like that.
Isn't that like still dangerous stuff?
Well, and so, yeah, you don't really want to be having your fingers where that spark is, because you could burn your fingers. But you're welcome to play with it. You can generate very high voltages that way. That's actually the way high voltage pulse power supplies work. You can take something like a battery, just has 1.5 volts or something like that, but then have an inductor interrupt the circuit and get a very short but high voltage pulse coming out, and use that to power high voltage pulsed devices. Yeah, so that's one example of an RL circuit. We'll look at some other, probably the more common example, the LC circuit, we'll look at next time.